Alright guys, welcome to today's class, and let's get started with the class today. Today we're going to continue where we left off and pursue similar congruent triangles, right? So let's get started. Let's start with 3.6.3. Prove that if the three sides of a triangle are equal in length, then all three angles of the triangle have measured 60 degrees. Why is that going to be true? Alright, let's see. We have this triangle with all of these sides to be equal, alright? There we want to prove that they're all 60 degrees, or these angles are all equal. So we can draw perpendiculars. Now, since these are, this is half, these angles are going to be equal, all right? Remember, why? Why is that true? Because this is an isosceles triangle. Because these two sides are the same, so it's going to be these two angles are equal. All right? Because if we drop the perpendicular, then it's going to be these two equal. All right? So these sides are the same. We can just prove it by SSS. All right? We can just draw the median. Now we can do the similar arguments for the other angles, and we can get these two angles are the same, these two angles are the same, and these two other angles are the same, or that all the angles are the same, but the sum of the angles in a triangle is 180 degrees. Divided by 3 is 60 degrees. That's what we want to be. Prove that if three angles of a triangle are equal, then all three sides of the triangle have the same length. Note that for this problem, you are not allowed to say that triangle is equilateral as you prove. You must prove the facts about equilateral triangles that you learned in this text. Alright? I'll take another try on B, and I'll tell me answers through chat. Well, let's get started with this question now. So we want to prove that these three angles in the triangle are equal, then all three sides are the same length. Same exact proof, but in the different congruency formula, right? Okay, buddy. So we'll get started. So these three angles are all the same. So if we split it down, say we draw the altitude, right? These are going to be 90-degree angles, but we also know that this side is equal to itself. So you go by AAS that these two triangles are equal, all right? This triangle and this triangle. These two triangles are all equal. You're going to repeat this proof for the other triangles, different altitudes, and you'll get that these all three sides are the same. Same exact idea as the A, all right? Now let's move on to 3.6.4. Two angles of an equilateral triangle have measures 3x plus 27 degrees and plus 2 and 2y minus 4 degrees. Find x plus y. I'll just have a try on this question and tell me the chat. Let's get started with this question now. So, how would we approach this? Well, since it's an equilateral triangle, all the angles and the sides must be the same. In this case, we're given two angle measures. So we know 3x plus 27 degrees is equal to 2y minus 4 degrees. Alright? And I want to make this kind of like equivalent, alright? If we want to find x plus y, we have to make it so that these two have the same exact. Well, we want to sum it up actually. That's the hope. That's what we actually want to do. We want to simplify this for us, right? But also notice that the angles are also equal to 60. Alright? So one way to approach it, if you just don't want to solve for the angle, is just to algebraically manipulate, right? Another way is just to straight up solve for the angles. In this case, 3x plus 27 equals 60 degrees, or x is 11. And then you can solve for y. 2y minus 4 equals 60, or y is 32. Oh, wait, no. Yeah, it's 32. Y equals 32. And finally, oops, adding this all up, it gives you 43. Right? I also want to 3.6.5. Point O is the center of the circle in the diagram below. Find AOB if OAB is 70 degrees. Let's get another try on this question and tell me this is true. And notice that it's an isosceles triangle. Just so you know. Because all radii in the circle are equal, right? So you have a try on this question and tell me this through chat. All right, let's get started with this question now. So basically, how do we do this? Well, notice that it's in a circle, and we all know the definition of circles, all right? OAB is 70 degrees. If OAB is 70 degrees, this means it's the base angle because every single radii in the circle are congruent. That's what you want to look for in geometry questions. Look for radii, look for lengths that you know, or angles that you know. This scenario, we have 70 degrees over here, which means that this is also 70 degrees, or AOB is 40 degrees, right? Let's move on to 3.6.6. It's a little bit hard. Triangle ABC is equilateral in the diagram below. DEF are in triangle ABC such that CAD is equal to ABE is equal to BCF, and D lies on CF, E lies on AD, and F lies on BE. Prove that triangle DEF is equal. I'll just get over trying this question and turn this to chat. Well, let's get started with this question. So, we know that DEF is equilateral, right? So we know that CAD is equal to ABE is equal to BCF. We don't have we don't have we don't have like the size that much. So we don't need to assume the size that much, or we can use sides for the similarity proofs. But we're not gonna use sides that much, we're gonna focus on the angles, right? Notice that point DEF is on the triangle since CAD is equal to ABE is equal to BCF. Alright. One way we're gonna approach it is just so that these sides are the same. We want to prove that these triangles are all the same. How do we prove that? This angle is the same. These angles are indeed the same. There's one side that's the same. And we know that all the angles are 60 degrees. So this angle is also going to be 60 minus that angle. But we know these angles are all the same. So these angles are also the same. From here, we can use by AAS or ASA, if you want, AAS or ASA, that these scalene triangles are all congruent, which means that these sides are equal. And then from here, you can realize that since these sides are equal, it's going to be AE, the equilateral triangle is going to be DA minus AE, but AE is equal to BF, which is also equal to CD. DA can do the same exact thing. Is equal to FC. Oh, it should be equal to FE. Yeah, my bad. I meant B. Is equal to B, which is also equal to FC. And there you have it. That's how you prove it. Right? Now let's move on to 3.6.7. In the diagram at the right, VW is equal to VX and WX is parallel to YZ. Prove that WY is equal to XZ. Prove that the YX is equal to WZ. I'll let you guys have a try on A and B and tell me answer through chat. All right, let's get started with this question. So notice that WX is parallel to YZ. And we want to prove that WY is equal to XZ. Well, how do we prove that? Well, since these are isosceles of each triangle, we can prove using similarity by AAA. Well, we can't prove it right now by AAA. But we can prove that these angles are equal by because they're parallel. These are parallel and these are transversal. So AAA follows, and these are equal so that these have the same exact ratio. So from there, you can deduce that WY is equal to XZ. And we can prove that YX equals WZ. YX is equal to WZ with a similar fashion. Right? You can prove the congruency between WVZ and uh YXV. Right? Now we want to go over construction. How do we construct this? Well, you can construct an equilateral triangle using two circles intersection. Oops. Two circle intersections. And you can draw a perpendicular bisector with it also. Right? Now let's move on to 3.7.1. Given a segment AB, divide the segment into four equal pieces you with a straight edge and a compass. Well, how would you do this? Well, you would draw this line first, and you draw a circle. Now you draw the circle with the same exact radius over here, and then over here, and then you make a perpendicular bisector on each of these circles. Right? This doesn't isn't really accurate math, it's just a simple sketch what you could do, but this will give you all four equal pieces. And this is divide segment into AB. Alright. Or you can use you can do a perpendicular bisector here, and then use this and draw a circle and draw another circle and make a perpendicular bisector there. That's your second piece, and you do the same thing for the other piece. Right? Is it necessary when constructing the perpendicular bisector of AB to use circles with radius AB? Suppose we draw instead two intersecting circles with center A and B and the same radius. Is the segment connecting the 2 points where these circles meet the perpendicular of AB? Well, the construction will still work. Why? Because these the orientation does not really matter. I'm gonna do this. I want to draw the perpendicular bisector of AB. Well, these circles will still intersect. And we can draw radiuses that they are collinear and then drop the perpendicular bisector. We can prove that this by SSS. You can give a head and go get it try by yourself, but this is still possible. Now, how would you construct a 90-degree angle? I'll just gonna try this question in summers through chat. Well, let's get started with this question. So you can easily construct this. You can just draw a perpendicular bisector, of course. Draw the perpendicular bisector, and there you go. That's your 90-degree angle. Now a 30-degree angle. That's a little bit harder. But how can we do this? Well, you only know how to draw an equilateral triangle and a perpendicular bisector. But we need to know that. We know that. An equilateral triangle, every single angle is 60 degrees. So what if we draw a perpendicular bisector of an equilateral triangle? Alright, let's see. You can draw a circle. I don't draw the best circles, right? Now with this, you can draw a perpendicular bisector. Now that's gonna be a 90-degree angle, but this a perpendicular bisector of an equilateral triangle. Remember, a perpendicular bisector of an isosceles triangle will always be an angle bisector too, which splits the angle into halves. So this will be a 30-degree, and this will also be a 30-degree. And that's how you do it. Right? Now what we learned today is SSS congruence, SAS congruence, ASA congruence, and AAS congruence, and also some similarity tricks, right? And then what we use is corresponding parts of congruent triangles are congruent, such as ABC and triangle ABC and triangle DEF. Corresponding parts of the congruent triangles are congruent, right? And a triangle in which sides are length equal isosceles, three of them are equal, it's gonna be equilateral, right? And we can construct perpendicular bisectors and equilateral triangles using compass and compass and straight edge. And if a radius of a circle bisects a chord of the circle that is not a diameter, then the radius must be perpendicular to the chord. Now, if it was a diameter, then it could either be, if it was a diameter also, if you draw this, if you draw a diameter, the radius can be any degrees. But your radius can be any degrees, right? Because this is just basically half of a circle, so you can have any degree, so it won't be perpendicular, right? But if it's a chord, that's a different answer, right? That's it for today's class. I hope you guys have a wonderful weekend, and I'll see you next week. Bye.